Let's talk about sequences and series, which are a core part of IB Math AA, both SL and HL. For this topic, the SL and HL content is actually the same, so no need to worry about what you do or don't need to know. A sequence is just an ordered list of numbers, like 2, 4, 6, 8, and so on. We can label the terms in the sequence like this. U1 is 2, U2 is 4, U3 is 6, etc. Sequences can be either finite, for example the sequence defined as 2, 4, 6, 8, or infinite, the sequence of all even numbers defined as 2, 4, 6, 8, 10, and so on up to infinity. We can write a sequence by listing each term, as we have done up to now. Or we can use a general term, which is written as un, where n is the position, also known as the index, in the sequence, which defines the value of un for any given n. For example, we can write un equals 3n, which would be the general term of the sequence 3, 6, 9, 12, and so on up to infinity. In a way, we can see sequences as a type of function, just like the ones we're used to, but simply a function from the natural numbers instead of all real numbers. A function f defined by f of n equals un, where u of n is our sequence. This is all neat, but sometimes we don't have an explicit formula for the sequence. Instead, we just know what a term is in relation to the previous one. Hence, we can also write the sequence in a recursive manner, by writing un in terms of un minus 1, as long as we also define a first term u1. Otherwise, we would just end up stuck in an infinite loop. For example, this same sequence we've been looking at can be defined by saying u1 equals 2 and un equals un minus 1 plus 2. Now, onto the second part of this topic, series. Series are just what you get when you add the terms of a sequence together. We often write series as S of n, which represents the sum of all terms of some sequence un up until n. So, if we stick with our good old friend un equals 2n, we can write the corresponding series, which is S of n equals 2 plus 4 plus 6, and so on. With that sequence, u4 equals 8, and s4 equals 2 plus 4 plus 6 plus 8, which equals 20. More generally, for any sequence u, S of n equals u1 plus u2 plus u3, and so on, all the way up to n. You also need to understand sigma notation. Really, it's just a compact way to write repetitive sums. We'll use the big Greek letter sigma to represent a sum, which we now know we can also call a series. The way it works is we have some variable with an initial value, which is written under the sigma, and a maximum value on top of the sigma. Finally, after the sigma, we are given the term to sum as a function of the variable we defined under the sigma. Therefore, we can write any series in sigma notation, based on the sequence it is the sum of. As an example, here is the sigma notation for the series we just saw a second ago. It's really not too hard, but you do need to be able to understand and use it in the exams. Just like sequences can be finite or infinite, so can series. And guess what? You can still use sigma notation to notate them. Now, you may be wondering how infinite series work, or why they're useful. After all, if you keep summing things, it's always going to go to infinity. Or is it? We will look at a specific example later in the video, but more generally, it's important to know that infinite series, sums of infinite sequences, can either converge, when they progressively get closer to a certain value, but more often than not, they diverge, which means that the sum goes to infinity, or doesn't settle at all. Maybe it's always alternating between 1 and minus 1. For now, we can think of infinite series as just what happens when we keep adding terms on and on and on. But later in the course, we will learn about limits, and see how we can define them more rigorously as the limit of S of n as n goes to infinity. Great! So now that we know what sequences and series are, we can look at two specific types of them, which are very important in the IB syllabus. First are arithmetic sequences. These are sequences with a constant difference between terms, like 3, 7, 11, 15. The difference between all these terms is 4. We call that common difference d, and thus we can write the nth term of any arithmetic sequence in the recursive notation we learnt earlier. There is also a formula to help us find a term without knowing the entire sequence. Intuitively, this should sort of make sense. We take some number, and then we add d a certain number of times. And the reason it is n-1 times rather than n times is simply because, for our first term, u1, we don't need to add d. The first term is just u1 on its own. We only need to start adding d for all the other terms, hence n-1 times overall. We can also have arithmetic series, which, as the name suggests, are just series based on arithmetic sequences. There is a formula that allows us to get the sum of the first nth terms. And, as we've just seen, we can replace un by the general term of an arithmetic sequence, which gives us this second formula. And to decide between the two formulas, we just need to look at what information we have. If we know u1 and un, then we use the first formula. If we know u1 and d, then we use the second. They really are equivalent otherwise. However, clearly an infinite arithmetic series would never converge, because if we just keep adding d, however small it is, we'll just keep growing at every term and eventually diverge to positive or negative infinity, depending on the sign of d. The second type of sequence and series we need to know is what we call geometric sequences. These work kind of like arithmetic sequences, but we multiply by a common ratio instead of adding a difference. So for example, 5, 10, 20, 40, each term is just multiplied by 2. So we can find our recursive formula, just like we did for arithmetic sequences. And we also have our general term. And again, it's n-1 there, not n, for the same reasons as earlier. This should all hopefully make sense. Now, we can also have geometric series, which, as you may have guessed, are just the sum of terms in a geometric sequence. And thankfully, we also have a neat formula for it in terms of u1 and r. Geometric series are where infinite series start being relevant. Indeed, we are multiplying by a common ratio to get to the next term each time, which seems like it should diverge to infinity as well. But what if we have a common ratio less than 1? Then each term will get smaller, which means the sum of the terms will eventually converge, since as we go to infinity, each new term is basically 0, meaning the sum is virtually unaffected. In fact, this also works with a negative common ratio, but it is fairly rare. If this is the case, we know our series is convergent. But convergent to what? Well, if we take our formula, and imagine n growing larger and larger, then since r is less than 1, it will get smaller and smaller as n gets larger. Hence, our formula just reduces to a simpler form, which allows us to find the value to which an infinite geometric series converges. But remember, you always need to check r is less than 1 first, otherwise this formula will not work. And that's basically the whole topic. You should now know how to recognize and work with arithmetic and geometric sequences, how to find general terms, use summation formulas, and interpret sigma notation, as well as knowing when a geometric series converges and how to work with convergent infinite geometric series. That's it for sequences and series. We'll see you in the next video, which is about exponents and logarithms. Should be fairly straightforward, but always good to get a refresher.